Hi everyone. Welcome to the third class of this particular subject, Kinematics of Machines. Again, we are going to learn about relative velocity method only, which is one of the graphical method. And this time, in this particular session, we are going to learn about what is meant by Coriolis acceleration component, and then we are going to solve one problem related to Coriolis acceleration component. Coriolis acceleration component means normally if any acceleration is measured with respect to any fixed point, I mean any stationary point, that acceleration or that particular link will be having two types of acceleration. One is radial acceleration, another is tangential acceleration. This we already know. The radial component of the uh, acceleration acts along the link. The tangential component of the acceleration acts perpendicular to the link. But this components are for the acceleration which is being measured with reference to some fixed reference point. But when the reference point itself is moving, I mean when the reference point is not fixed, then the total acceleration will be expressed in terms of these three components. It will be having radial component, tangential component, and Coriolis component of acceleration. So here we add one more component of acceleration which is called as Coriolis acceleration component. And Coriolis acceleration component exists when slider moves along moving link in normal mechanisms. For example, you can consider crank sorted river mechanism or a rotary engine. Here the slider and link, the other link pair, will not be fixed, so they will be moving with respect to each other. So there, in such type of mechanisms, Coriolis component of acceleration acts. So please remember that this Coriolis component of acceleration acts only when the link on which the slider is moving also is not fixed. I mean that link itself is also moving with certain velocity. So let us consider the expression, or how to derive or how to calculate this Coriolis component of acceleration. So consider a simple link connected to ground by a turning pair as I have shown here. So this link AO is connected to ground by a turning pair, and on that the slider B is moving along link OA. So I already told the Coriolis component of acceleration exists only when the link which is associated with the slider also moves. So here OA is also not fixed, it is rotating with certain angular velocity, and on that B is also moving with certain linear velocity. So suppose if I turn this link by say an angle d theta, and B is also moving with certain velocity. Now there are the three stages of motion for slider. One is the slider moves from B to D because of angular velocity of link OA. So the slider moves from B to D because of rotation of OA. Then it also moves from D to E along link OA because of velocity V of slider along OA. So along OA, the slider has got velocity V, so that's why it moves from D to E. Then the slider moves from E to F because of acceleration of link perpendicular to OA. Acceleration of link perpendicular to OA. So because of that, it moves from E to F. Now this third component, the motion of this third component from E to F is due to Coriolis acceleration. And how we are going to derive what is the expression for this Coriolis acceleration. So let us consider this EF. This EF is given as CF minus C. So that's what I have written here. Now CF is an arc and it can be expressed as the radius OC into dt. So that's what I have written, OC into dt. Similarly, CE is nothing but it is equal to BD, and BD is OB into d theta again. So that's what I have written here. So if I take d theta in common, it is OC minus OB into d theta. And if you see here, what is OC minus OB? This one is OC and this one is OB. It is nothing but BE, BC or DE. So DE into d theta is the expression for EF. Now, if you consider DE, it is nothing but the motion of slider along link OA, which can be expressed as displacement multiplied by so velocity of slider multiplied by time. So V into dt, and omega is equal to t theta upon dt. That is, the angular velocity is given as rate of change in angle divided by the time taken. So d theta upon dt. So hence d theta is given as omega into dt. So I am going to substitute this d theta and d in this equation, d into d theta. So I will get EF as d, which is v dt, and d theta, which is omega into d theta. So I will end up with this equation, v omega into dt square. Now comparing this equation, this above equation, EF is equal to v omega dt square into uh, with s is equal to ut plus half at square. This is a common kinematics equation where you can assume u is equal to 0, the initial velocity is 0, so the ut will cancel, s is equal to half at square. So when we compare this equation with this equation, I conclude that the Coriolis component of acceleration is 2v into omega. So that's how I have calculated, or I have arrived at the expression for Coriolis component of acceleration. Now, these are the sign conventions which are used for Coriolis component of acceleration. Just see here, when the signs are, all signs are in positive directions. I mean, the slider is moving in positive y direction and counterclockwise direction of the link OA is also positive only. Then FCC acts in negative x direction, and similarly, if all are acting in opposite direction or in negative direction, I mean here the acceleration is velocity of the slider is downward, that is negative, and clockwise, that is also negative, then also the co-release component acts on negative x direction only. But in other condition, where if the angular acceleration and the linear velocity of the slider have different signs, then it will be acting in positive x direction. So this is how we provide sign convention for Coriolis component of acceleration. Now let us solve one problem related to Coriolis component of acceleration. So this is the problem statement, which is a quick return motion mechanism of a crank slotted type. So this is crank slotted lever mechanism where OA is fixed and its length is given as 25 centimeter. AB is of length 10 centimeter, and there is a slider here, and OC length is given as 40 centimeter. AB length is given as 10 centimeter. CD is given as 15 centimeter, and angle OAB is given to you, which is 120 degree. And this angle, the crank AB is rotating with the uniform speed of 60 rpm, and these two are perpendicular to each other, OA and the line of stroke of D. What is asked is you need to determine velocity and acceleration of CD. So here is the problem statement, the rough draft diagram which has been given the problem statement. So we need to convert this into configuration diagram. The scale which I used is 1 centimeter. I want to take it as 10 centimeter. So first thing what I have done is I have drawn two parallel lines which are 45 centimeter apart. That means in our scale 45 centimeter means 4.5 centimeter apart. Then I have shown the vertical line OA on that, like this. So this is OA of length which has been mentioned in the problem statement, and then I have drawn the crank AB, which is 1 centimeter, and the angle is also mentioned to you, which is 120 degree. Now through this point O and B I have drawn a straight line, and the length of OC is also known to me. So I have reduced it to the required scale and I have drawn OC. Now using divider, I have drawn an arc of length CD to the reduced scale and then joined CD, and that's how I have completed the configuration diagram. So I already told you how to draw the configuration diagram for earlier example also. So in the same way you have to do it for this one. So let us proceed. Now I need to draw the velocity diagram, and for that what I got is the speed of link AB only. The speed of link AB is given as 60 rpm, and we know already how to convert that into angular velocity. This is the formula 2 pi n upon 60. So using that I have converted it to 6.28 radians per second, and hence I can find out the tangential velocity at point B using this equation. So VAB is equal to RAB into omega AB, where RAB is length of the link AB, which is uh, 10 centimeter, that means zero point 0.1 meter, and we already calculated omega AB, so that's what I used, and I got the answer as 0.628 meter per second. So this is the vector which I need to show it first, but before that I need to select an appropriate scale. So I am going to take 0.1 meter per second as 1 centimeter. So the scale which I have selected is 1 centimeter is equal to zero point 0.1 meter per second. Now I need to show the vector VAB, which will be perpendicular to link AB. So draw a line perpendicular to AB. So this blue line is the line perpendicular to AB, and on that point make 2 points which are at a distance of 0.628 meter per second apart, or to the reduced scale 6.3 centimeter apart. So that's what I have done. I have shown 2 points A and B. Since A is fixed point, that also represents O, which are 6.3 centimeter apart. So this, and see the arrow here, as AB is rotating in clockwise direction, I need to show the arrow in this direction. So this end will be B and the other terminal will be A and O, both are fixed points. So that's about VAB. Now let us draw the other lines. So here the link OC is there, and the tangential velocity at point E, uh, which is on link. See here, I have considered B as a slider here in this particular case. Uh, so here point B is a slider and point E is the point on link OC. So for point E, if I want to determine the tangential velocity, it will be perpendicular to OC. So draw a line perpendicular to OC, and similarly if I want to find out the velocity B, that B velocity is along link OC. So that's why I have drawn a line parallel to OC, and the point of coincidence of these two lines is nothing but point E, and complete the velocity polygon. Now to proceed further I need to determine point C, and point C is the point on link OE or OC. So I already have vector OE, and as I already know, for in configuration diagram the ratio OE upon OC will be proportional to the OE upon OC on the velocity diagram. So based on this theorem, determine the length of OC and show it. So that's what I have done, and from point C draw a line perpendicular to CD like this. So this line is the line which is perpendicular to CD, and if you consider point D here, it is moving horizontal to with respect to the fixed points O and A. So draw a line, horizontal line from point O. So I have drawn a line or a horizontal line from point O. This point of coincidence is nothing but point D. That's what I have shown, and complete the velocity polygon. So I have done with velocity diagram. Now let us determine the unknown quantities. So all these are the quantities which are required for further analysis, that is acceleration, to plot the acceleration diagram. VOE is 0.3 meter per second, VDC is 0.2 meter per second, VBE is 0.42 meter per second. So with this, let us proceed to acceleration diagram, for which I need to draw a table. If you compare the table with the earlier example, one more column gets added here, that is Coriolis component, which will be there only for the link which has got slider, and that link is also moving. So here this OC or this BE is that link. So here BE is the link which is also moving and which has got Coriolis component. So let us start with link AB. The length is known, velocity is known. We can calculate radial acceleration easily because it is the ratio of v square divided by r. So that's what I have done. And the tangential acceleration for this link AB is 0. Why? The link is rotating with a uniform velocity 60 rpm. So that's why the tangential acceleration will be 0, as alpha is 0 here. And it has got no any Coriolis component. Then OE, if you consider its length, we can easily measure using the configuration diagram which we have. OE length is not given, but it can be measured through this configuration diagram, and it comes as 0.31 meter. So in actual scale, it might come as 3.1 centimeter. When you convert it to your scale, it will come as 31 centimeter, and I have converted into meter. It is coming as 0.31 meter. And velocity we already know for OE. That's what I have written here, and I have calculated the radial acceleration component. But for this I cannot calculate tangential acceleration component because alpha of OE is not known to me, but I know the direction in which it acts perpendicular to OE, and again this one has also not got Coriolis component. Now line B is actually a point as of now. B is slider, E is point on link OC. So it has got no any radius, but its velocity is given. It is OE. V is of velocity 0.42 meters per second. As r is 0, the radial component of acceleration will be 0. The tangential component which we need to calculate, it will be parallel to OC. As the velocity is along OC, obviously acceleration also will be parallel to OC only. And here for this link, these 2 points BE, we have got Coriolis component also, which is given as 2V omega. 2 V is already given to you 0.42 omega. You need to calculate omega B, you need to calculate based on VB. VB is 0.42. You know the formula, V is equal to R omega. This formula is given to you. So based on that, you need to calculate omega B, which comes as 1.967 radians per second. So based on that, I have calculated Coriolis component of acceleration, which is coming as 1.22 meter per second square. Now CD, link CD. For link CD, the length is given, velocity is given. We already calculated this velocity also, and radial component of acceleration is given by this formula. And again, tangential component will be perpendicular to this link CD, and its magnitude is unknown to us. So with this data is sufficient to draw acceleration diagram. So just go through these values and set an appropriate scale. If you see, the maximum one is 3.94 and other are very small ratios here. So what I will do is I will take 0.5 meter per second square as 1 centimeter. So I am going to consider 1 centimeter as 0.5 meter per second square. So let us start with the first one. I will draw a radial component of acceleration for link AB, which is 3.94. So when you reduce it to our scale, it will become 8 centimeter. So draw a line of length 8 centimeter, which is parallel to link AB. So this line is the line which is parallel to link AB, and on that line I need to show 2 points which are 8 centimeter apart, and I need to draw vector A dash. See the arrow how I have shown here. It is always away from fixed point A or O. So both of these represent fixed point, and this one represent a dash, and the vector a dash represents radial component of acceleration for link AB. Now the tangential component of this link AB is 0. That means there is no tangential component. That means this A dash itself will be AB. So that's what I have shown. This A dash itself is AB. Now let us proceed to next line. Here, here in this link, we know the radial component, we know the direction of the tangential component. So first draw the known quantity. So for OE, we know the radial component of acceleration, which is 0.29, and when you reduce to our scale, it becomes nearly around 0.6 centimeter. So draw a line parallel to OE from point O of length 0.6 meter. So this is a line which is passing through O, and this line is parallel to OE, parallel to OE, and on this line I need to show a line of length 0.6 meter. So that's what I have done. So here OO dash indicates the tangential radial components of link OE. For other link, for other component of acceleration, I know the direction only. I don't have its magnitude. So just draw a line perpendicular to AO dash, and this line indicates the direction in which the tangential component of link OE acts. So let us proceed further. For BE, the parallel component or tangential component of OC is unknown, but we know co-release component, and this one acts perpendicular to link B. So always draw the known quantity first and then go for unknown value. So the known quantity is this one. For this we know the value also, and we know the direction also. What is the direction of this component? If you see in this velocity diagram, the vector B is acting in upward direction. Vector B is acting in upward direction, and link OE is rotating clockwise direction. So clockwise direction is negative, upward direction is positive, and hence the co-release component of acceleration acts in positive x direction or in right side. So I will draw a line parallel to, sorry, perpendicular to link OE. So this is a line which is perpendicular to link OE, and on that line I need to show a line of length 2.44. 1.22 is actual scale. When I reduce it to my scale, it will become 2.44 centimeters. So that's what I have done, and I have marked it as B dash B. And if you see, the arrow is pointing right side. So this is the known quantity. Now for others, for tangential component, I know it is going to act parallel to OC. So this is the link OC, and parallel to that link the the tangential component acts. So draw a line parallel to OC or perpendicular to BB dash. This point of coincidence, which is common to these both these links, is a common point among these, that is point E. So that is point E, and complete the acceleration diagram. Now I need to mark the acceleration diagram for CD also, but for this one I cannot look, I haven't located the point C also and point D also yet, but I can easily point the locate the point C based on the same theory which I used for velocity diagram. So here how we have marked point C, if you remember, in same way we need to mark the point C on this diagram. I have got vector uh, AE, which I have shown here. So join point A and E, you will get vector AE, and point C will lie on the extended version of this line AE. Use proportionate scale and mark point C. So I know the point C. Using this point C, I can easily find out. I can now draw the tangential component and radial component for line CD. So if you see the radial component which acts parallel to line CD, which is 0.6267, when you reduce to our scale, it will come around 5.1 or 5.2 centimeter. So draw a line parallel to CD and make a point, mark a line of length 0.52 centimeter, 5.2 centimeter, as I have shown here. So this C dash C is of length 5.2 centimeters. Then the other component of acceleration, that is tangential component, acts perpendicular to this component. So draw a line perpendicular to this. One more thing is, if you come to consider point D is moving horizontally with respect to fixed point O and A. So draw a horizontal line which I have shown here, and the point of coincidence of this normal and this horizontal line is nothing but the point D. So that's what I have shown, and I have completed the vector polygon. In the question which has been asked here, what we have to determine is the acceleration of point D, which is equal to AD or OD, and it comes as 1.7 meter per second. So that's how we have to draw velocity and acceleration diagram for uh, the mechanism where slider is moving on a link which is also showing certain movement. The link which consists of slider is not fixed, that is also moving with certain angular velocity. So in such cases we need to consider coordinates component, and we have to draw the acceleration polygon. So that's the end of this problem. I have given one practice problem again. Practice it. I have mentioned the answer also. So please practice it. And thank you. If you have any questions, please mail us at the mentioned email IDs. Thank you once again.